I'm excited to be here today, and my sincere thanks to the organizers. It's a very different audience than I normally speak to, and I'm keen to get to engage with all of you. But I'm particularly excited to tell you about the fact that there's work going on right now that is about to render the most advanced kinds of tech that we have, things like this, the equivalent of pre-industrial technology in the next decade or so. I'm going to tell you a little bit about the work that goes on in my group, in my field, and I'm going to tell you about how this new generation of technologies that we're building called quantum technology is going to have tremendous disruptive impacts on business, on the economy, in society, and I'll tell you a little bit about some of the efforts that have been going on in the last few years of industrial engagement in this research field. In order to do that, I need to start with a math problem. So we're going to do one together. Here's the challenge. I want you to tell me what are the two prime factors of a number? What are the two numbers divisible only by one and themselves that when multiplied together give you the number on the left? So what are the prime factors of 15? 3 and 5. You want another one? How about that? You're right. What about 21? 3 and 7. Awesome. You guys are good at this. One more. How about that? So you laugh because it looks ridiculous. But the fact is, the only reason you were able to do the other two easily was because you memorized the answers when you were kids, right? You memorized multiplication tables. That problem that I just showed you, as simple as it looked, is actually provably difficult for any computer. That means something very specific. But that difficulty of that problem for computers, carried out to this extreme, where the number you're trying to factor is really big, is pretty much the basis of how all of our online transactions work today. All electronic commerce, all secure financial transactions, we just heard about fintech, which is heavily reliant on this. All of our inter and intragovernmental communications that are secure rely on things called public key crypto systems. RSA is one of the most famous. Maybe for your bank, you get sent something in the mail. It's an RSA token, right? That's generating a public key for you to log into your website or whatever, where the security comes from the difficulty of that math problem. That even supercomputers find that problem really challenging. All of that is about to change because of this guy. His name is Peter Shor, and in the mid-1990s, when he was at a place called ATT Labs, which is now no longer in existence, he's now at MIT, he posited that if you could build a computer that behaved differently than the computers we use today, differently than even supercomputers, a computer that used the physics of quantum mechanics in order to represent and process information, then you could write an algorithm that could solve that problem efficiently. Now that's tremendously important because it says that what we've used for the past decades to do secure communication in all sorts of realms, from security to finance, now may no longer be secure. This sparked huge interest from pretty much everybody, and immediately after, in 1995, big government organizations in the United States, in particular the National Security Agency, the NSA, got involved by starting their first ever university research program, funding university academics to engage in the question of whether this kind of computer could actually be built. This is called quantum computing. And this is the field that has grown up tremendously since the 1990s, and my career has grown alongside of it. So there have been so many developments in just the last 18 years or so that now the NSA is no longer asking the question in a very speculative way, is it possible to build this kind of computer? Instead, they're issuing directorates like this from the IAD, which oversees the so-called NSS, the National Security Suite of Commercial Algorithms Used for Information Security, where they say the potential impact of adversarial use of a quantum computer is known and without effective mitigation is devastating to the National Security Suite. This is not a joke agency. This is not quantum consciousness kind of stuff, right? This is the premier security agency in the United States saying that this kind of technology is about to render useless the kinds of encryption that have been used for decades. And really what I want to talk about for a few minutes is how we can realize this kind of computational power. What is it that can get us to the point where this is reality? Because we're really on the path. A lot has changed since I entered the field in about 2001. Well, to understand that, we need to understand a little bit more first about how our current technology works. Really, everything that you would have heard today or in the last couple of days at Pause is predicated on the kind of technology we're employing in data centers and laptops and mobile phones based on controlling electricity. All of our technology works because of our ability to control the flow of electricity. This is how data farms work. It's how server farms work. It's how everything else around us works. And of course, at the core of these kinds of systems are things like this. This is a photograph that maybe you've seen before. These are microprocessors. These are devices that allow us to process information by controlling the flow of electricity. We build special switches called transistors because these devices are based on a class of materials called semiconductors. Semiconductors are materials that allow electricity to flow like a conductor, like a wire, or to act like an insulator, such that electricity doesn't flow, depending on the application of another electrical signal. Controlling the flow of electricity with electricity is what makes all of our technology today work. And that capability, which has obviously been so profoundly impactful on our society, fundamentally comes from our understanding of quantum physics. Quantum physics is what makes semiconductors behave the way they do. Maybe it's an underappreciated fact, but it is one that's really important. These things are really quite astounding. You literally fit 1 billion of these transistors, of these electrical switches, on a chip about the size of your thumbnail. This is a remarkable bit of engineering. But what's really exciting to people like me is that our leveraging of the quantum world in this kind of technology is extraordinarily rudimentary. The way we build this kind of technology is a little bit like building these things. You start with a big pile of stuff, and you gradually shape it into what you want. Now, we can do extraordinary things by learning the right rules. We can learn how tall the sand pile should be to make a sand sculpture. We can learn how wet or how dry the sand should be in order to make a particular form. We can make beautiful, extraordinary structures. Just like we can build structures with literally billions of transistors on a chip the size of your thumbnail. You can do really extraordinary things. But it should not escape your understanding that if instead of looking at the giant pile of sand and what kind of sculptures we could make, if we changed our perspective and we were able to look not from this very high level, but at the smallest scales, that there's more to be used. That if we could now, instead of seeing the giant pile, we could see the individual grains of sand, that there's a new level of complexity that emerges that was previously not visible to us. Now the sand is not a homogeneously tan pile of brown stuff. Now you see that there are bits of shell and bits of crystal. You see that there are different colors, there are different shapes. None of this was visible to you when you were building technology just by looking at the giant pile of sand. And so what's going on in our community of researchers is that we're asking the question, can we take a similar approach to the way we build high tech? Instead of looking at the giant pile of sand, can we look at the individual grains of sand? Can we go down and look at the most fundamental building blocks of matter to start building technology? Can we start here? Can we use this cartoon representation of an atom as the fundamental building block for tech? Can we start all the way at the bottom? And before any of you object to the notion that this is absolutely ridiculous to start building technology one atom at a time, well, here is a picture from my laboratory of one atom of ytterbium. That's a photograph. We shine on light, just the right color. It bounces off. We take a picture with a camera that's not dissimilar to the one in your mobile phone. That's one atom trapped in something called an ion trap, a special electromagnetic bottle. We can trap one, we can trap many. This is from work my group did in collaboration with NIST in the United States. Each blue dot is one atom, here of a different species called beryllium. The atoms organize themselves into these neat crystalline arrays. We're effectively building matter one atom at a time. And again, this is a real photograph. This is a picture of this kind of technology. What's exciting, going back to this question of individual grains of sand, is that there's a new level of complexity emerges when we start building technology this way. Because when we get to these scales, when we're talking about technology built with single atoms, the familiar rules of physics that govern our daily experience give way to a strange new set of rules that we call quantum mechanics, quantum physics. Here, the picture that we have of atoms like billiard balls that bounce off of each other or bounce off the walls of a pool table has to be replaced by a picture in which we conceive of them a little bit more like waves. Waves that spread out in space through something called quantum superposition. Waves that interfere with each other or with themselves. Nature on these scales even appears to possess its own form of magic. There's something called entanglement that allows particles obeying the rules of quantum mechanics to be linked together no matter how far apart you separate them. You can separate them by the distance of the known universe. You manipulate one and the other will instantly feel that phenomenology. This is physics that is completely glossed over in today's technology. None of this is in use. In fact, for decades, some of the greatest minds of the 20th century thought that this was nothing more than strange math, that this was not real. Even Einstein very famously referred to entanglement in a pejorative sense as spooky action at a distance, because he thought it was bullshit. But he's wrong. We know that this physics is real, and we can access it in our labs, because now we can see the individual grains of sand. We can access individual atoms, and we can use that as the starting point for building technology. A few years ago, a colleague of mine wrote an article in which he said new technologies based on the exploitation of so-called second-order quantum phenomena, such as quantum entanglement, deserve a public-friendly, rational, and sexy name. Spooky technology is that unifying term. Now, for good or for ill, spooky technology has not caught on. This was from 2007. But quantum technology as a concept has really matured. And I will assert to you that the development of quantum technology, harnessing this weird physics as technological resources, will be as transformational as harnessing electricity was in the 19th century. If you think that's a bit overwrought, and I'm selling you a bill of goods, let me show you this. This is a picture of something called the NIST F1 atomic fountain clock. Has anybody heard of an atomic clock? This is one of those. This is a fundamental piece of technology that uses quantum physics, the quantum physics of superposition in atoms, in order to gain a very precise and regular tick. A clock that ticks with the same period over huge timescales. In fact, this clock is good to about a second in 80 million years. The new research grade clocks are good to about a second in a billion years. Now, you may scratch your heads and say, well, why do I care? I'll be long dead before I lose a second. Which is true. It's true. But that capability to have a clock that's so regular and so accurate is what has given you global positioning. If any of you have engaged in the last couple of days with a location-based service of any form, if you came here using Uber or did a check-in somewhere, you were relying on quantum clocks to make global positioning systems work. If somehow that does not impress you, then the same application, quantum clocks, is what makes the internet work. Because the internet requires what's called wide area network synchronization. Networks where one clock is ticking at the same time as another. That comes from atomic timekeeping instruments, quantum clocks. This is only the first application that's been developed for quantum technology. And think about how the internet and global positioning have changed the world. So hopefully you're on board with me now. The question now is, where do we go in terms of realizing this kind of quantum computing technology that I started out telling you about? This is a picture of a supercomputer from Oak Ridge National Labs. It's called the Titan. It has extraordinary performance. It's the kind of system that's broadly used for solving problems in physics, in climate modeling, in basic material science and the like, nuclear reactions. This is one of the most advanced pieces of computing hardware that exists today. Let me contrast that with this picture I showed you before. Again, a picture of individual atoms. There are about 300 here. in this particular device from work that my group did in collaboration with the US a few years ago. Now, in this work, we were able to encode information on all these atoms and get them to run an extremely simple algorithm. Really, really, really simple. The kind of quantum equivalent of does 1 + 1 = 2. Nothing useful, but a first step. This system had about 300 atoms, as I said, and according to the rules of quantum mechanics and the way we encode information, with 300 atoms, we simultaneously can represent 2 to the 300 numbers at the same time. 2 to the 300 is about 10 to the 100, which is a googol. It's a number so astronomically large that if you tried to build a supercomputer, like the one I showed you a moment ago, with the same computational capacity, the same ability to represent these numbers, you would run out of matter in the universe before you could build that computer. And here you get the same kind of capability using about 300 atoms. This has obviously been really motivational to many people seeking applications in the space, right? You can't build a computer bigger than the universe. You can build this other one. So the applications that have been developed over the past few years, I won't go into them in detail, but they range from optimization problems for logistics to search problems in energy, problems in chemistry, biochemistry, the simulation of physical systems as deployed for energy use and distribution, and of course, as I mentioned at the beginning of the talk, information security. Now, these applications have been profoundly interesting to many researchers, but now are becoming interesting to big industrial players. And over just the last couple of years, what we've seen is a change as we've shifted from an entirely university-focused effort with global interest and tremendous strength in Australia, that's why I'm here, to tremendous engagement and capital injection from some of the world's largest technology companies. In particular, here I highlight Google, IBM, and Microsoft, all now engaging in the development of quantum technology, in particular quantum computers as one application. Now, Microsoft has an investment at a few universities, including the University of Sydney, where I'm based, mainly going to my colleague David Riley. Google and IBM have taken similar paths, that they've started with kind of academic research, but now all of a sudden what we're seeing is enormous influx of capital. Microsoft talking about kind of 8- and 9-figure investments over the next few years in this kind of research area. The interesting thing that's happened very, very recently, because say IBM and Microsoft have long had quasi-academic research initiatives within them because they're very big, is that we've seen a big shift towards the emergence of startups in quantum technology, in quantum computing in particular. Here I highlight two, one called Rigetti Quantum Computing and one called IonQ, which is run by a colleague of mine at the University of Maryland and uses the same kind of individual trapped atoms that I've shown you throughout this talk. This is just a highlight of a couple. There's real rapid growth and interest in this field from venture capital in particular. And the truth is that early investors have the opportunity to totally shape the trajectory of technological development for the next 50 or 100 years by getting in this. But in order to do it successfully, they need to cut through the cacophony of chatter about this technology right now. Because right now, people are smelling blood in the water. They're seeing the money pouring in at levels that are completely different than what we get in academic circles. And they are lying their asses off about what can happen here. This is really challenging because venture capitalists who rightly want to make investments here now need to sift through much of the chatter that really truly runs the risk of destabilizing the market. Because people are promising developments on the timescales that VCs are accustomed to from mobile applications. Now, this is really different because this is an actual picture of a quantum computer based on trapped ions running a program. It's one of the most advanced systems. This image was taken by my postdoctoral researcher, Cornelius Hempel, when he was at the University of Innsbruck, one of the real global leaders in this field. That, about 20 quantum bit system, if you squint a little bit, maybe looks like that. It looks like a 1950s technology for computing with things that blink. The important thing that we should keep in mind is that all of the innovation that we experience and enjoy today in software, in mobile, in digital, comes from decades of development in hardware. Hardware that changed incrementally. The same is true here. Investment in quantum technology, and quantum computing in particular, is a hardware problem. These are decade time frames, not 2 or 3 month time frames. So it's important to remember that. But something that's very exciting and motivational to me is that when we look back at the history of computing in particular, we see that the most profound impacts of these new technologies are for the problems that were least anticipated and the new applications that were least anticipated. Quantum technology has the potential to completely change everything about our economy and society by revolutionizing our ability to process information, just the way we've seen the same happen in the past. So I was excited to get to share this vision with you, and I hope you enjoyed hearing a little bit about the future of quantum technology. Thanks very much.
If you don't mind, is there a couple of questions? We'll take a couple of questions before going on this break. I'm too scared to ask. This guy is too smart for me. Yeah?
In terms of, I guess, VC investment and money pouring into the industry, is it the case it's just a race to the finish, that the one organisation will find that one solution and become the next, the future IBM? Or are there multiple solutions that multiple beneficiaries?
I think it's a great question, really asking about is there one path, or are there multiple paths to innovation and success in this field? First of all, exactly how to build the hardware is not clear. So my group and IonQ use trapped ions. Other people use circuits made of special superconducting materials called, well, aluminum is the one they typically use. These approaches have strengths and weaknesses, but nobody yet knows which way is going to work. Right? It may be some combination of various approaches. The fact is we're really very early in the development of the hardware in order to really pick a winner. That said, we're reasonably sure that these things are going to work. And the kinds of approaches to computing that we run on the different platforms, because IBM now has an online cloud-based system called the Quantum Experience. The way these things run is the same between technologies. And so there still is an opportunity right now for early stage investment in software associated with eventual quantum computers. Just like Peter Shor, when he developed his algorithm, he didn't even know if you could build these things, but that algorithm still works on all of these pieces of hardware.
And we'll take one more here.
Hi, I don't know if any applications are already being considered, but I imagine that the huge power of analysis that could come along could radically change something like analyzing DNA, which is currently very complex, especially for an entire genome. Is that something being looked into?
Yeah, absolutely. There are two parts to that. One is there's a known algorithm on quantum computers called Grover's search algorithm that shows that unstructured search can be efficiently solved using this kind of system. So if you have huge data sets with no indexing, you just need to search. And then the other one is that there has been a lot of work showing that complex biochemical processes, which are difficult to understand because the chemistry is governed by the quantum interaction of electrons, can be efficiently solved using similar systems. So people are thinking about protein folding in particular as one application.